All right, welcome back to the SciMax channel and the playlist on electronic lab notebooks. Last time I showed you the self-driving lab light demo. That is a remote instrument we can run and control by Python. And we did a very simple experiment in one dimension. We just varied the blue LED and measured an output, and then used an interpolation scheme to optimize the value to get a set point. Today we're going to expand that idea and go with a more traditional design of experiments. So I show in the figure here, this is a Box-Behnken design, and you can use this in a surface response where we can have all three variables changing, R, G, and B, and then we have an equation here that we look at a quadratic surface. So I'm going to show you how I use Python to set up this design and how we use it to automate running the experiments, and then at least a preliminary kind of analysis. All right, so that's there's three kind of knobs we have to turn in our measurement, and that is the R, the G, and the B intensities, and then we measure 8 different sensors at different wavelengths, and our goal today is to find an RGB setting that set these three channels to be 10,000 each. That's just an objective that we've chosen. So we saw previously that at least the blue channel is slightly nonlinear. It's mostly linear in B, maybe a little bit of quadratic or cubic behavior. And so we're going to take advantage of that knowledge here and use a design of experiment to map out the space in all 3 dimensions. I'm going to use the PyDOE3 package, and this package has a little bit of history. You can see up here that PyDO3 is a fork of PyDO2, which is itself a fork of PyDOE. So the original PyDOE was sort of abandoned, and some authors picked it up and made PyDOE2 to fix some bugs and add some features. And PyDO3 is similarly a fork of PyDOE2 because they were having trouble getting bug fixes and things. We're going to use it because it has a convenient tool here for BB design. That's Box-Behnken design. We can tell it to make a design for 3 variables, and I'll make a pandas data frame here to represent it. And so when you run this, you get a design that looks like this. So we have run number or experiment number in the index, and then we have these coded variables for -1, -1, 0. And these variables are coded -1, 0, and 1 for the most part in this design. And those are coded for low, medium, high levels. So 0 is a middle setting, -1 is a low setting, +1 is a high setting. And we have to convert these coded variables into actual levels in our experiment. So we have 15 experiments, and you can see these first 12 are all different. They're actually the red dots in here. They represent these spots on this cube, and the last 3 are a center point at the middle. And we have replicates of that, so we have 3 replicates at the center. And that helps us understand some of the variance and noise in our measurements. It's unclear, like in advance, if this is enough. This is just a starting point. Okay, then I have to convert those -1 and 1 into a range, and I do that by setting min-max values. So previously we knew that the answer to get 10,000 on the blue channel was about 50. We'll make an assumption here that the value we want for R, G, and B is going to be near 50, and we'll do our experiments in the range of 25 to 75. And then we can map the coded values into real values with this formula down here, and I convert them to integers because we have to send integers in our experiment. We can't set floats. All right, and so here I use pandas syntax and just create R integer, G integer, B integer as columns, and that gives us this new table down here. So you can think of this as experiment number in the index, and we need to get the intensities from 25, 25, 50, 75, 25, 50, and so forth. So we'll do 15 experiments, and then we'll be able to do some analysis on those. All right, so let me run that. I used the same kind of code that I used before in the last one. This is the most minimal example of Python code that you can use for their self-driving lab demo. We get a client. I'm going to cache the results. So here we're going to cache the JSON data that comes back. And I use an optional label so that we can run this multiple times by using unique labels. And then we just use a regular measure function that will get the results, and it returns the 3 numbers that we're interested in. Okay, and the way this works is just like this. If I run measure 50, 50, 50, then it gives me the 3 numbers that I care about, and it would be nice if these 3 numbers were basically like 10,000. So I don't know. Let's have a little fun and see. We'll do these one at a time. They take about 7 seconds to run, sometimes longer. And I don't actually have to do these one at a time, so I'm going to speed this up a teeny bit. We can change them like this. So we need to make this one more like 50. Let's try 58, 44, and 42. Okay, that seems like about as close as we're going to get. I think if I go much lower than this is probably going to drop down below. But this gives you an idea of where we expect an answer to be. And it also gives you an idea of how boring it is to manually do this. All right, so we're going to keep this number in mind, 44, 59, 36. That gets us close to 10,000, 10,000, 10,000. All right, let's run the experiments. When we run these experiments, we should randomize the order. That's important because when you do things in sequence, you can get artifacts from that sequence. So for example, let's say we were ramping up in sequential order and the LED gets hot and hotter and hotter and hotter. Then we can't separate the effect from it getting hotter with the effect of it being in sequence. And so you randomize that so that you get it as a nuisance variable that should average out more effectively. The easiest way to randomize this from the data frame is to just sample it with fraction equals 1, and this is going to shuffle the results, and then we'll get a randomized order like this, and then we want to run these in this order, like so. And so we just need to iterate over these rows. So that's done down here. So I'm going to iterate over the rows and do a measurement for those conditions. And then we'll store the index and the output. And then we'll make a new data frame down here that shows the results. Now I've already run those, so we're just looking up a cached version here. So these are the results from the different runs, and they map onto the inputs above. All right, I like to explore the data a little bit, and one way we can explore it is to look at the center point. Here we find out where the center points are, and we can look at the outputs there and see, are these reproducible? These ones are all about 12,000, all about 8,300, all about 12,300. So those look pretty reasonable. All right, the next, I don't know how to look at the other rows in any reasonable way. You might average or something, but we're going to skip that. So let's make a model now. Let's say that our model idea is that the output is simply linear in the input. That is, I have an RGB, and the output for the first one is, say, A0 times R plus A1 times B plus A2 times G, and likewise for the other ones. That is going to be just an input vector times a matrix, a 3 by 3 matrix of parameters that we can solve for. We have 15 measurements, 9 parameters. We can solve this in a least squares way. And we do that with this simple np.linalg.least squares. Simple linear model, linear in each input. And the output supports that statement. We have large numbers on the diagonal and basically 0 numbers on the off diagonals. So if we neglected these, we would actually have a pretty good simple model that only the R value only depends on the input of R, the B value only depends on the input of B, and so on. Okay, we can make a parity plot to see how good it looks, and it doesn't look, it's not perfectly straight. We see there is noise, and there's noise in the data, but it shows here that we have roughly parity, and at least within the noise you see here, you would expect a decent prediction. Now that model is simple. We can invert it and calculate what value would give us 10,000, 10,000, 10,000 for if we know that's what we want, what input would give it to us. And here it says 41, 58, 34. I already forgot what we found manually. Manually, we got 44, 59, 36. So these are reasonably close in values. And if we run this, we get something that is, close to 10,000, but not exactly 10,000. And that's a feature of the noise in our model, that there is uncertainty in the model because we don't have enough terms describing it. And that's because we forced a line to go through data that might not be totally linear. And we saw it is not totally linear before. It might have a little curvature to it. So we can try a little bit more sophisticated model. Here I'm going to use the quadratic model that we alluded to at the beginning. So we use 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. And this includes the linear terms in R, B, and G, the pairwise terms, and the quadratic term. So I use sklearn preprocessing polynomial features to generate those. We set up a polynomial features degree equals 2. We make a feature matrix here. And actually, let's see. Let me make sure I told the truth here. This has 6 columns. So this actually doesn't have, what if I make this false? If I make this false, then it has the quadratic term. And now we have 9 parameters to solve for. And if we look at the parity plot, you can see here that there's much less noise. So we get interactions and the quadratic term, and we get a much tighter fit in there. So this is clearly a better model, which is not surprising. It just has more parameters. And now if we want to find the input that gives you 10,000, then we have to do this objective optimization problem to find the input that minimizes the sum squared error between input and 10,000. So let me go back to what we found manually. Manually, we said 44, 59, 36. And what we find by our design of experiment is very close to that. And if we put this into our measurement, Then this will take a few seconds to run. We get numbers that are probably within noise of 10,000. So here I'm going to test that by running it 10 times. That is unfortunately going to take about a minute, a little over a minute probably. And obviously I changed something, so this is going to run in real time now. It's hard to tell something's happening here. That's why I normally write these in for loops with TQDM so that you get the visual noise that something is happening. Here we don't get any indication anything's happening because I wrote it as a list comprehension. And so we simply have to wait. Looks like it finished. So M here should be an array of 10 measurements. So I'm going to plot the histogram of these. You see the red one's quite tight, the green one's quite tight, and blue one is pretty reasonable. We can look at the average. The average of these is close to 10,000. The standard deviation is quite small, actually. And if we look at the 99% confidence interval, the upper bound is close to 10,000, but not exactly 10,000. Plus or minus 2 standard deviations is often regarded as like approximately a 95% confidence interval. Okay, so overall, this was a very bare bones DOE approach. It was formally DOE because we used the Box-Behnken design to set up the experiments, then we ran the experiments, and we fit simple linear and linear polynomial models. What we didn't do is any analysis of variance. We did not look at sensitivity analysis or uncertainty quantification, and so we still we're in the neighborhood of where that solution is, but we may need another round of experiments to refine exactly what the neighborhood for that solution is. And I'm going to leave that for another day and say that this video is basically done. The most critical idea in this today is, how do we take this design? How do you get this design? I got it from a Python library. You could have typed it in yourself. You might have decided to use random sampling or other kinds of sampling. And eventually we might take this into an active learning approach where instead of running these 15 experiments, you might decide to run a more active learning approach and get to the solution rather than run all of these, fit a model, and get to it. It's not real obvious what the benefits of it are. There's benefits both ways. If you do this design of experiment, you have a more proper statistical way of treating analysis of variance that you lose when you do active learning. But active learning may get you to a solution with fewer experiments. And so those are the kinds of things that you would want to think about. All right, that's it for today. Come back next time for the next episode.